All right, now that everybody is tired and full, no one can argue. This is the best way to give presentations. So I'm going to talk about performance monitoring. Not going to talk about ATS until the end, about strategies for integrating and what I feel like we're leaving out. I'm going to give a really quick overview of performance monitoring, how it used to work and why it doesn't really work very well that way, and the kind of things that we can do now because computers are fast. And then I'm going to talk about open source libraries for tracking that stuff and APIs and how we might integrate them into ATS. So we will be fighting octopuses, disposing of bodies, and investigating time. So I know that as like software engineers, most of the time we obsess about performance in an unhealthy way of like tracking instructions and tracking ticks on CPUs and latch contention or lock contention and multi-threaded performance and blah 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 blah. But in the ATS community, particularly, what you do actually touches users directly in the browser, right? So like when someone clicks to play something or load something or show an image or show a page, every time you add 100 milliseconds to that, you're an asshole. So don't do that. So a lot of times, if you look, I don't know how many people have seen graphs like this, probably stare at them until our eyes bleed. You have this kind of goal, like every asset we deliver should be delivered within 1.5 seconds, right? So 1,500 millisecond delivery time. We're tracking, how long it takes to deliver messages, and the world is wonderful because we're always beating our objective. So this is an average. And if you look at this graph here, this is 24 hours. So it's a 24-hour long graph from noon to noon. And as one can imagine that like this little line right here is, I don't know, probably 200 milliseconds. That's probably about 4 minutes worth of data right there, right? Because you don't have enough pixels. You don't have 86,400 pixels here, so it's certainly not every second. But I don't know, how many assets do you guys deliver in 1 minute? 4 minutes. One. It was one asset. It was 200 milliseconds. The world is great, right? So it's not that. It's actually probably somewhere around 10,000 assets or 100,000 or maybe even 1 million assets that you delivered. Depends on what size they are and how busy you are. So you have to kind of ask yourself, what does that 200 milliseconds mean? Jack shit is the answer. Doesn't mean anything. A long time ago, I think engineers realized that, and they took us a huge leap forward into quicksand with the concept of percentiles. So instead, what you do is you track, say, a 99th percentile of some sort of operation. So now what you know here is that, okay, at that same point in time, actually, that's 900 milliseconds. But now we sort of know what that means. That means that however many requests we served in that time frame, 99% of them were faster than 900 milliseconds, and 1% of them were slower, right? So there's a deep bench of fatal flaws with both the implementation of this and the model of this. So the first flaw is that there are very few systems out there today that actually track the 99th percentile correctly. So if you look at the popular telemetry libraries that are out there, the ones that are in like Dropwizard, there's some that are in Go. So like Golang's, what's that, Go metrics. There's a Coda-Hail Dropwizard metrics now. There's one in Python as well. They use all of these really interesting techniques for doing reservoir sampling and displacement in the samples that come in that window. So you actually don't have an accurate understanding of 99th percentile. The best case scenario is that you have a tremendous amount of traffic in that time frame, and you get some sort of sampling that gives you some sort of confidence around how accurate the 99th percentile might be given random sampling and replacement. But if you have, say, so the way those tend to work is that, say I have like 1,000 buckets, and as a new measurement comes in, I randomly replace one of those buckets. So when I look back on it, I should have 1,000 recent samples in there that are a moderate, representation of my overall sample space. So the real problem is if I'm doing 100 requests a second, at the end of the time frame, I'm guaranteed that at least 900 of those samples are not from the time frame I'm looking at. They're old, right? And if I have that window big, that happens all the time. And if I have the window too small, I have a really inaccurate representation. So most people who do sampling collection of like latencies, they're flawed that way. So the other thing that this doesn't tell you, which is that's kind of an implementation detail. You can fix that problem just by not being stupid. But the other problem that you have here is that, and this tends to be a little hard to explain if you're not familiar with statistics and looking at percentiles. But this number, right? We have a red line on that screen that seems to be important, right? It's 1.5 seconds. That's our service objective. The problem is that you have no idea what the difference between these two numbers are, because you're not subtracting here. So the best analogy I can give is, let's say you had a school of students, and as the principal, you really cared that the students were doing well, and you had some sort of alarming threshold that said, you know what? No more than 5% of our students should get below 60% overall scores. Right, so you're tracking that along, and then suddenly you're graphing what the 5% are getting. 5% are getting 75s, everything's great. And then it drops to 60%, then to 59. So now you're in a situation where you know you're violating your objectives. You know that 5% of the school is getting 59%, 59% or lower, right? So you're violating the objective. There are two questions you can ask. One of them is, how bad are we doing? Which is, how bad does the 5% mark doing right now? 59%, right? That's kind of a dumb question, because when you ask how bad are you doing, you're actually questioning how many of our students, what percentage of the population is failing, right? It's the 5% you carry as the variability, not the 60%. So here, what we know is that 1% of our traffic is slower than that. We also know that 1% of our traffic is slower than this. Is that 1% slower than 1.5 seconds? No idea, right? So you have absolutely no idea how many users are having a bad experience given that sort of graph. So, fuck, right? Like that's a bad problem. So that's kind of manifests by a lot of the metrics and telemetry packages out there. They do this sampling. And then instead of sharing that wealth of sample data, they actually share the 99th percentile only. So you're tracking this 99th percentile number through time, and this is actually the only data that you have. You don't have the original samples that were used to construct this. So the huge problem there is that because you have a variable arrival rate in these windows, right? This is not the 99th percent sample over a million requests, a million requests, a million requests. It's different over time because you're servicing at variable rates. So in the middle of the night, you're probably doing less traffic than you are in the middle of the day. So the 99th percent is a percentile of a different base number. So fundamental problems, it looks like the problem there, we have like two service violations that we could consider flapping, right? We've got this one and this one. This was a close call. And then we totally screwed the pooch, right? So at 3 a.m., everything broke and life was horrible. So a quick kind of rundown of percentiles. So everybody's seen a histogram before, I'm sure. This is actually a latency histogram of one of our nodes. And what we can see here in our database, right? So like 99th percentile is 149 microseconds, right? So what that doesn't tell you is what the worst one is, right? So given a histogram, you actually know that, right? You have all of the samples in there. You can see how fast was the fastest, how slow was the slowest. You can actually calculate the median. You can do an estimation of the mean. The other things that you can do that are awesome without looking at the 99th percentile and things like that is by looking at the histogram, you can see that we have modes, right? We have 1, 2, 3, 4, 5, 6 modes that are apparent in the system. What does that mean? Well, it means that you should be very concerned if it changed. So understanding the modality and seeing a shift in modality, right? So if you had an origin server that went slow, you would develop a new mode for all the traffic that's hitting that origin server in ATS world. So occupy the 99%. the big problem with all of these percentages is even when you're achieving your goals and your 99th percentile is lower than your objective, you don't know what the state of the other 1% is. Is it I'm lost in a tunnel? Is it I'm dead of something, the plague? Or am I being eaten by a dragon, right? Like all of those things, those different levels of badness aren't construed through that metric. So, and then you have this problem conflated, right? So if I look at the black line here, so this is the number of actual users showing up. Everybody has this information and when they monitor a traffic server, right? It's the total number of requests derived over time. So you count the number of requests, figure out the difference between 2 points in time, and that's your requests per second. So the number of requests per second are going through here. We have a huge spike right here, right? And then we actually have one of the lowest parts of the whole day is actually during our outage. So when you look at 99th percentiles and things like that, a lot of times this information is really lost. So I'd rather have a catastrophic outage when no one's on my site than a mild service problem when everyone's on my site, right? That should be obvious, but when we look at the percentiles for trying to establish QoS objectives, very rarely are those two things put together, so we're blindly troubleshooting bad 99th percentile QoS when it actually doesn't matter at all, or matters a lot less. So, what does that look like? The interesting part is that if you look at, in a histogram, if I zip back to the histogram real quick, this one, right? So if I actually store a histogram of the data and I decide 100 microseconds is my service objective, I actually can count all of the different samples that are bigger than that. I can count all the samples that are lower than that. So instead of asking how fast was 99th percentile, I can say what percentile was at 1.5 seconds or 100 microseconds. So I can invert that question because I have the data source. So this is sort of inverting the data source. And the top graph is actually the percentage of people that violated the 1.5 second boundary, which is a much more interesting data source, right? You can see that there are little blips all through here, and I'm short. You can see all those blips through time, which actually tell you that things were not good, right? There are certain times where this is flatlined at 0, and that's fantastic. That means that every single service request that I performed was under my service level objective. But that's not the case. Even though that line was happily under the 1.5 seconds, it's not the case all the time. So if I take that, and because percentages aren't, right, 40% of a billion is a lot more than 99% of 2, right? So if you look at how this is a huge percentage of people that got screwed, but there are very few people here. So it's a bigger percentage of a smaller number, whereas this little spike right here was at peak utilization. So when you multiply those two things together, you multiply percentage by a population, you actually get the percentage of population affected. And this is what that looks like, right? So we thought that the outage was there, but that time where we were kind of jogging around our service level objective, we actually just screwed a whole bunch of user experiences. So that's what typically people look at. This is actually the integral of that, so the discrete integral. So we're counting the number of unhappy users. It pops up there, pops up there. We actually screw just as many users between here and here as we do between here and here. Right? So that's kind of an interesting, this is real data off of a real web service. How often do you think you have one of those super embarrassing outages at 3 a.m.? Hopefully not often, right? I mean, like you have one once every 2 months and everybody talks about it over lunch. How often do you think you have normal service during the day? Right? So every single day of the month, you're probably screwing as many people during the day as you had during that accidental outage at night. It was just that one day, you screwed twice as many people. Because we're measuring those things incorrectly, right? We're looking at that data, we're looking at a summary of that data that actually isn't informative to ensuring like individual user experience out of the front end. So that's really interesting. And it seems kind of easy on the web side of things to do that. I mean, how many requests per second do people actually serve? Does anybody here like sustain more than 5 million requests a second all day, every day? I don't know. One? Close to that, right? 5 million is just a really small number, right? So what if I told you that all of that stuff, if you could do it on user experience, you could do it on low-level systems type of stuff, right? So the things that you worry about as engineer, like latency on acquiring a lock in a thread, being context switch off your processor really sucks. So how many nanoseconds of context switch time do I have? Okay, so now you're in the 5 million a second range, not the 5 million a day range, right? But you can still apply all of the same techniques because all of our systems are fast enough to do this now. So the way we've always done this, because like performance profiling is super awesome, that's performance profiling, right? So I get what time it is, I do my thing, I measure what time it is again, I take the difference, and I record that in some way. I should probably not use log because every mathematician will be like, why are you taking a log of that? You're logging it out and recording it. I should probably change that. So the interesting part is one of the fundamental differences between measuring something that takes a really long time, like servicing a web page, as opposed to a really short time, like involuntary context switch or context switch in a kernel, is that suddenly telling what time it is becomes significant. So one of the problems that we ran into when we started pushing this down stack, we wanted to track the latency of every database operation that we do in our system. So we run a telemetry company. It has ATS in front of it, and the ATS stuff is the least of our problems. All those problems happen behind. So how do you measure how long it takes to do a database operation? And if your database operations are aimed at 1 microsecond per operation, that means that how long does it take to figure out what time it is, right? So figuring out how long it takes to figure out what time it is on Linux takes about 86 nanoseconds to figure out what time it is, right? So if it takes, is it 86? No, it's 120 something, 125 nanoseconds. So if you do like a clock get time high res or something like that in Linux, and you just do it in a loop as fast as you can't do more than one every 125 nanoseconds or something like that. So if you look at that, turns out 125 nanoseconds is not an inconsequential amount of a microsecond. It's like 12.5%, right? So if you do 2 of those, you're now at 25%. You have a 25% observational bias that's introduced into the system. So there's certainly limitations until like actual clock time on operations and CPUs are exposed as first class through the processor, like virtualization extensions were and things like that. So there's some limits to that. So when you probe things, the first thing that you want to do is make sure that you don't have latency bubbles, you don't introduce latency bubbles by performance timing them or recording them. That includes having no allocations. Obviously, you're not going to malloc while you try to time something that's fast. And then you want all of the operations to be order 1 operations if possible, right? So you want the amount of observational bias introduced into the system to be incredibly consistent and predictable, so that you don't add variance, you just add kind of penalty. So one of the things that's I love this stuff. So we wrote this thing. It's open source. It's BSD licensed to make time measurement faster. So we were able to get about a 200% performance improvement over Linux's nanosecond timers, all in user space. And I don't know, we don't have anything in ATS right now that would really benefit from that because we're not doing timers of things that are microseconds long that I'm aware of. Most of the things we're doing are timers of like origin requests and things like that, which are super slow in the millisecond range. 1% overhead is not a big deal. But yeah, we dropped that to a fixed number of instructions on a fast path, and it takes around like 48 nanoseconds now to figure out what time it is. So that's useful. But more interesting than that is how do you record it? So we released all this stuff open source, which is what I would recommend using to do some more advanced telemetry collection out of ATS. Libcirc metrics, unlike the title would imply, it doesn't actually have anything to do with Circonus services at all. It's just a simple API. It doesn't talk to anybody. It's data structures for storing timing information and general statistics. So it was a little bit inspired by the stuff that we saw in Go when we started doing Go metric stuff. They had some interesting, clever tricks in there. One of them, which is really neat, in a lot of statistics systems, you end up registering a statistics system, and then everywhere you want to account for stuff, you've got to go add code in those places. Well, it turns out that people have code in those places, and they have variables in those places a lot of times. So like global connection count on a server, for example, might be in a global variable in the process. So one of the things that you can do in the namespace, you create a name in the namespace and attach a data type to a pointer in memory. And when you go assess that, it just looks at the memory. So you don't actually, you just register kind of like that uint64 at this pointer address actually contains the metric that I'm looking for. So it's completely passive. No code gets introduced anywhere else for those simple types of metrics. Other things that end up being a little bit more hot in the system. So that's really useful for gauges, like when you're counting like a steady state of things. The other thing is strings. So being able to observe like the ATS version string. If you have the string as some sort of const char star somewhere in the system, you can just say, hey, the version is at that pointer address. So you don't actually have to do anything around where the version stuff is established to register it into the metric system. The histogram stuff is really interesting, and the counters are really interesting in that they do automatic CPU fan out. So if you're logging them, it'll have, I think 256 different counters that get incremented. So it'll fan that out to reduce lock contention around those. All that stuff uses atomic lock contention instead of pthread mutexes. Same with the histograms. They also do fan out. And then when you go to actually observe what the values are, it will iterate and combine and reduce them back to their steady states. So it's really fast. The most important part is that the overhead for logging into a histogram is 10 nanoseconds and it's fixed. It's 36 instructions. So there's a lot of work for that. If you have something that, there's kind of two modes that the histograms run in. One of them is a pre-allocated mode, which builds kind of like a two-level page table to do the inserts, and that's the faster version. Ends up being around about a kilobyte of space. But if you have something that doesn't need that sort of really fixed low-level performance, you can use one that only takes up about 20 bytes of space until you start adding new bins into the histogram. That one can malloc in certain cases. So you'll pay overhead every once in a while. So for things that are infrequent, where you're doing millisecond level timing, it's better to use those. If you're doing something like tracking context switches, you would establish the slightly larger one, and it would just have no mallocs during the build process. And then there's an internal API that will dump all of that stuff as JSON data. And there's two modes for that. One of them is to dump kind of the super aggregate set of that, and then there's another one to dump since the last snapshot. So you can get incremental snapshots of what's happened. So that's that. The API is super simple for that. It helps us fight the technology octopus. But the important part is that this graph is actually a D3 representation of the JSON output of that stuff. So all of this stuff, as the representation's all open source too. It's in the web console for the metric stuff. So the idea of being able to see this on any arbitrary piece of the system that you're working on, like every cache insertion and retrieval from every spindle. If you can imagine doing that, you would immediately be able to tell when you have a performance anomaly against one of the spindles in your cache servers, right? So you have wear leveling issues, and suddenly your SSD has a new mode that gets introduced. It's like those things are completely absent when you're looking at averages. They tend to be incredibly misleading when you're looking at percentiles. So when you get these robust histograms, you actually have really strong insight into new emergent behavioral patterns in the subsystems.
What bucket size are you using for your histogram?
So the histograms use a fixed log linear bucketing system with 2 significant digits base 10.
Okay, so they get wider as the...
Yeah, so you can see this one's kind of faking it out a little bit, just in the visualization. But what we have is we have 89 buckets between 10 and 100. And then we have 89 buckets between 110 and 990.
Right.
And so it's 1.1, 1.2, 1.3, and then 11, 12, 13, 14, all the way up to 99. Like that. And it supports negative numbers, so half the key space is almost never used, unless anybody's serving stuff in negative amounts of time. Yeah. The implementation is pretty small and tight. And as far as I know, we're one of the only monitoring systems that actually can take the histograms and actually store them as first-class citizens in the database. So it's kind of cool to be able to produce histograms in ATS and then not be able to do anything with them at all because you're not running Synchronous. The APIs around the histogram stuff also have quantile calculations, inverse quantile calculations, estimated means, and things like that. So if you're not running the Synchronous product and we do the integration of ATS, you would additionally kind of do the crappy version of that and say, yeah, I had this histogram. What is the 99th and 99.9th and 75th and 50th and 25th and 0th and 100th, and get like those 6 kind of quantiles out of it and track those in a monitoring system because every recording system can track those.
What do you use for modality detection?
There isn't an API for that in the library, so we do that on the server side.
Right, after post analysis.
Yeah, so Brendan Gregg has a post on that on doing, he called it M value, which is an estimated 2 times the number of modes in the system, which is interesting when you get odd numbers out of it. But we have a variant that looks sort of like that. It has a lot of nuances to it, though. It's kind of a hard problem, mainly because when you have this one, this one's easy. This one is exceptionally beautiful in that every peak is actually a peak, except for 2. So this one right here, you can see this goes up and then goes down before it goes up again.
Right.
So Brendan's would see that as 2 modes, right? So there's some other data science junk that smarter people than I do figure that out in our system.
It's essentially a signal processing job.
Yeah. Yeah. And so it ends up being what you do is you isolate what you think might be a mode. You generate a modal distribution, like some sort of distribution that best fits the majority of the curve, and then you subtract and then you repeat. Is sort of the way it works. But it turns out that doesn't work super well either. It's kind of like a mix between all that.
I'm just wondering how, because if you have like thousands and thousands of these, how you would detect which ones have developed new modes or the modes have shifted to a significant important mode.
Yeah.
In an automated fashion that could alert somebody in ops to go investigate something.
So the way we do that is that we have modality detection that happens on histograms, and then we apply that modality detection and materialize it. So as the histograms feed in, they kind of loop back through our stream processor, and that produces a modality that's paired with each one of them. Mm-hmm. So then the modality detection, the modality is just like you'll see this would be like, server X database operation latency. There would be a server X database operation latency modes, and that would just be a number, and you could alert to its change.
Some sort of an estimation that fits each of the modes as an individual.
Yeah, and then you can do like more classic style anomaly detection on that. Figure out, you can do outlier detection, which is actually more important than anomaly detection in that case. Usually what you'll see, you have 2 types of modes that get introduced, right? You either release a new version of traffic server and you've introduced a new mode, you've codified a new mode due to some sort of performance regression or improvement. The other is that you have a system malfunction, so you have 1 node out of 50 that is not behaving like the others.
Yeah, I'm just thinking it would be really sweet to be able to do correlation between, if you have like the same mode shows up in 10 different subsystems, tracking down which one was the causal component.
You can, you could see the introduction of the new mode over time. Obviously, the modes themselves wouldn't actually align. A lot of times, the systems are much nastier than that, where the introduction of a mode in one place will remove 2 and add 2 for another node.
So in this request for identifying the long tail, basically instead of going with the percentage, but you're actually saying, look at the real worst case, affected and stuff. How much of, in practice, how much of noise do you think this adds? Because this is internet and there can be a number of things that can go wrong, right? It can be a bad client connection that's showing up in your, this bucket of long tail. And if you keep going after this rather than accepted 99%, where's the balance? I mean,
I'm not suggesting going after the long tail, right? If you want the long tail, you just track the 100 percentile, and you know that your long tail always,
okay.
right, in the system. I think the interesting part is the granularity of all of this data as well, right? So what does your lowest quartile look like? Between 0 and 25 and 25 and 50, and how does the behavior change and shift?
Yeah, I guess even for that, my point is that no one metric can give you a complete picture. You have to obviously correlate with something else to see what's causing it. So my point is, in practice, if you go after this rather than a more accepted 99%, how much of noise does it generate?
So the short answer is if you want a 99th percentile, you just run a 99th percentile transformation on this, and you're done with it, right? So this, in this case, this rich information would be distilled to 149 microseconds. That's it. And you just see 149.
I think
so
here is that looking at the 99th percentile lies to you about what's happening.
I agree, but I'm saying there is a balance you have to strike, because at some point there's something you can't really control.
Well, if you but
you spend too much energy trying to debug that.
I think the interesting part is that what I'm suggesting is that we actually start probing the latency of things that are important to the performance of the platform itself, including like request to origin. Those are really easy, and most people do that through logs today, right? They'll log every one of them and do it through Splunk, which is funding someone's retirement. So this ends up being really inexpensive to do, and if you don't want the information, I would say my point is that it's both inexpensive memory-wise and inexpensive computation-wise to collect it so that it's there if you need it, and you can be blissfully ignorant of it all the time if you want to. We've been doing statistical analysis on time series histogram for 6 years, and the amount of stuff that it uncovers is fantastic. So that right there, you may think of that as a lot of noise, but if I hand that to my database engineers and ask them, why does our latency profile look like that? They're going to have one of two answers. They'll have a 2-minute answer where they highlight the peaks and they say, okay, these are cache hits, right? These 3 different modes are different tail storages. This is a certain type of query, and this is another type of query that happen, like that are common in the system. Or they go, holy, it shouldn't be like that, right? And the problem is that 99th percentile will never give someone that it won't lead them to the next question. Right? This is not answers. This is fuel for questions in most cases. But most of debugging and performance profiling is a fuel for the next question. That's all I have. I'm probably way under time. But
are we over time?
20 minutes.
All right, so let me give you an actual example of something I've tried to do inside Traffic Server, which is instrument the event loop. So there's now Traffic Server, it's got the event loop, and we're having some issues with quality of service for one of our properties. They wanted certain latency guarantees. We couldn't figure out what was, we were looking at 99%.
Exactly.
We said we had to make their number work, but in order to figure out how to do that, the 99% was not very informative.
Right.
So I put some logging stuff into the event loop, and that's something I'm working on bringing into open source to instrument out basically just mins and maxes of stuff and counts of various values, and it was quite useful. I didn't end up doing histograms because I really didn't have that much. I wasn't willing to invest that much effort. But the issue I want to ask is, so I would limit the amount of time that I've been sampling. So I didn't want to look at any data that was older than 10 minutes. Actually, 10 minutes old. So because I didn't want the interesting data to get smeared out, right? If I sampled the event loop for an hour, you wouldn't, a lot of the interesting things, I think, would get smeared out and would just kind of look flat. Does that make any sense?
Only from averaging, though, right?
Yeah.
Well, if you're just having this histogram, each of those histogram things is an average. I want to see much more transient behaviors, right?
But they would pop up as a mode.
I mean, you're entering the realm of needing to store the histograms in time series, is what you're entering.
Yeah, do you age out? Is there any way to age out samples to make sure that I've only got...
We don't, so this is 100% sampling. So all you would have to do is, there's a snapshot feature in the library so that when you ask, you can tell it to reset itself while it's asking. So it always keeps a cumulative set, but then it keeps a single stream of snapshots. So you can go in and say, give me a transient snapshot and zero it. And they kind of accumulate in both. Doesn't work quite like that, but it's close. So then what you could do is set up, like, if you expose the JSON or have it write it out, if traffic server writes it out, you could just write it out every minute, and you would get only the previous minute of all 100% samples. So there's no replacement that happens in these histograms.
So there's so the time domain is whatever you want it to be, is what you're have it be the whole day in one histogram, or a 5-minute sample, or a 5-minute period, or 1-minute period, or a couple seconds. Would there be a good way to like that?
No idea. I highlight certain histograms to look at?
Yeah, like ones that are interesting.
No, I
go ahead and compare histograms and look for anomalies.
That's anomaly detection.
well, that's what we do at Synchronous. So no, it's not in the library itself, right? Yeah, so we do a lot of complex data analysis over time, like time domain analysis over histograms. You could load it in, I mean, most companies of size have a data science group that would love that challenge. So you give them, hey, I have these 4,000 streams coming out of traffic server, and here's the distributions over every minute of those 4,000 streams. Tell me what's up. And they'd be like, oh, that's an interesting problem. And then they'd dump it into R or Julia or something like that and kind of go wild with that.
If I had multiple histograms, if I was doing that fixed sample size, excuse me, can I easily add histograms together?
In the code, there's a cum function as well, so you can take two histogram objects and accumulate them together.
Okay, all right, that would work then.
Yeah.
So I could then just say, do a sample every second, and then when I want a minute, I could sum up the last 60 of them. That'd gives you a more rolling average, if you know what I mean.
So this is a product this is not ATS, obviously. This is a product that's internal to our system, and I can look. This should work the way you think. I get it? Okay. So if I can get it with the sockets. Right. So we have all of these different, this is an event loop. These are the file descriptors that are currently being managed. This is their masks. This is all coming out of the stats library. And then this is the histogram of this service call. So this C function. So it actually looks up the dwarf information on the pointer that's being called from the eventing system, and then has a namespace for each of those. So if I look, all of these are pretty interesting because they're all the same one. But if I look at this, I can see the histogram latency of that, right? So that's where all of the latencies are there, and I can see as I mouse over exactly what percentage it's what value and things like that. So see if I can get a better example of that with timers. So I have another one, right? So this is a different function that gets called back, and that's what the latency of this function is. So that's all. That looks like a relatively normal distribution, sort of gamma style. And I can see that. So it would be very, very easy to measure. Basically, every time you come out of the eventer with a certain mask and you're about to call that function, you find the name of the function, cache it probably, that's what we do, and then just time the callback itself, and it allows you to see when you've got a certain function that has an odd profile or a really bad set of outliers. Most of the stuff in this system is actually like, see if I can find something more interesting.
He also supports stuff like callout.
Call out?
Callout from the from Valgrind? The call timing output from Valgrind?
No.
No.
No. It's just a C API. So you register the name of the variable. It has kind of like nested namespaces. So you can say, give me a namespace called foo. Give me a namespace called traffic server. In that, give me a namespace called eventing system. In that, give me a namespace called callbacks. And then in that, give me 400 keys for all the functions we're going to call and a histogram for each one of them and accumulate. And then you'll basically get that. You'll get a JSON object that says traffic server, eventer, callbacks, and then a key for each callback in the system and a full histogram for the latency distributions. Yeah. So sure, I can pull up github.com/lab/ what's it called? libcirc metrics. Get Medulla. Yeah, I mean, it's a pretty straightforward API. I mean, it's documented. But it supports, it also supports maintenance functions. So for example, if you need to run something to calculate the value, you can register a function callback and it'll run that before it does stuff. Obviously use that with care. Those things only happen during that. It's all thread safe as well. So you can just have a dedicated thread that just observes, like produces the JSON document. Well, so. Any other questions? I think it'll solve your problem with.
Yeah, I think, I see how it could be done. That would be, that ended up giving a lot more data than I have now.
Yeah. Yeah. Every plugin hook. Yeah.
Well, you can even like every SM call out and every callback plugins.
Right. Yeah. I'm sure if you're not careful, you could produce a 200 meg JSON file every time you get it as well. But yes.
But at least for the
Yeah.
that's the slowest thing.
The JSON serialization also allows you to specify only namespaces. So you don't have to pull the whole thing. You can just pull an individual namespace and serialize it out.
Yeah, well, the biggest problems what Theo talked about initially is that I had to really work at the sampling to get it to not hose up the thing I was sampling,
yes.
Right? That's not so simple.
Actually, the biggest observational bias you're going to have is figuring out what time it is before and after your call.
Yeah.
So if you only care about, so I would steer away, if you're in the microsecond range for your callbacks, which you probably are most of the time.
Tens of microseconds, yeah.
Yeah, I would steer strongly away from get time of day, even though it's microsecond resolution. It's not actually on most systems. Like on Linux, it's not. It's updated. There's a reason that it only takes 40 nanos to call get time of day on Linux, because it's not correct all the time. You actually do need to use clock get time. And then you're looking at, I have a blog post on that, if anybody's interested in reading it.
It ends up using clock get time. I actually tried the monotonic clock, and it just seemed really flaky.
It went backwards, didn't it?
Yes.
Monotonic.
The monotonic did, the normal one did, but not very much. The monotonic, sometimes it just stopped for like 200 milliseconds.
Here's an article on why that happens, by the way. So we because we were monitoring a lot of really fast stuff, we had to investigate why it was taking so slow. At the bottom, we have the timing speed up. So on Linux, get time of day is 35 nanos because it's not millisecond. It's not microsecond level accurate. So it's a lie. Most people only look at like millisecond resolution timing with get time of day or second level, and it's fine there. The get HR time implementation, which is clock, get, which one is it? It's high res or clock real time? Clock real time, what it is. So the problem with clock monotonic is that on some implementations, I think that's fixed in modern Linux though, by the way.
rel 6.
Rel 6, yeah. There's two issues. One of them is that if you don't have invariant TSC supported in your processor, the tick rate, so the tick rate can change over time as you go into C state cycles. So if you go from C1 to C2 to C3, the number of ticks executed per nanosecond on the processor will change. And the processor only counts in ticks. So there's a little, if anybody has a flashback to elementary school in the US, y equals mx plus b, right? You need to figure out how far you are, you need to know how many ticks you have, the ticks per second that you have, and then figure out what offset when your processor booted. So each of the processors booted at different times, so they don't count. So if you just check the ticks, you check ticks on one processor and you flip to another processor, it's relative to a different epoch in the first place. So you have to be able to track the variance of all the epochs and the ticks per nano on all of the processors. So if you don't have invariant TSC on your processor, you're going to be slow as shit regardless, because the system has to serialize you onto a single CPU to get the answer. But if you do have invariant TSC, then what you end up doing is what we did. The only clever thing that we did is that we had cache-aligned spaces that store the y equals mx plus b, the m and the b values, right, for the processor. So when you call RDTSCP on Linux, it gives you, on Intel, it gives you the number of ticks that processor has seen since epoch, and it gives you the CPU ID that you're on. So what you can do is, in that single instruction call, which is really frickin' expensive, you get back the number of ticks, and you get the processor ID, and you hit a cache-aligned page that's for that processor ID, and guess what? You're the only one on that processor right now, so there's never contention. So you pull those two values out, calculate it, and then you store that nanoseconds since 1970 in there. So that's how we ended up doing it. But we got really good performance improvement. I don't know if we're ever, I'd imagine this shit's just going to make its way back into glibc in the kernel eventually. I know the FreeBSD guys are already moving this stuff back. You can see the real motivation of why we did it is because on Illumos, it wasn't 120 nanoseconds, it was 300 nanoseconds to figure out how many nanoseconds have happened. Which is just deeply insulting. But yeah. So if you're doing really, really high resolution timing, you should be relatively concerned that the 120 nanosecond, and that's on a processor with, that's like on an E5600 Xeon, which is Sandy Bridge and higher, should be at like 3.6 ticks per nano on that at a fixed rate. And if anybody's running ATS on a system with C states turned on, first thing you should do is go turn your C states off. Because so many bad performance problems can happen when C states are on a box. Anyway, I'm tired of talking now.
Is there any specific recommendations for ATS for this to do?
I think that the library is tiny, and it's BSD licensed, which I think is fine for Apache. To rely on it as an external library. It's super small, effectively one C file. And I would recommend like prototyping it in certain places. So all we would really need to make it easy, I think, is you could create a plugin. I don't know if you do it in a plugin. You might want to do it in Core. That has an optional URL that just JSON serializes the root of the stats tree. So that'd be the easiest first step. And then anywhere in the code you are, if you have that handle to the global thing, you can just say, hey, I'm interested in tracking this, so let's track this. And I think it should be minor code intrusion to play with it. So I wouldn't do it in master. I'd just do it in a branch and see what it looks like and see if it's as useful as I think it will be. I think it'll be incredibly useful.
We may try that internally. I'm actually tasked to port the event loop timing stuff, which is in R5.3 but hasn't been ported. So I'll probably try to look at this, see if we want to do that instead.
Yep. Cool.
Because it gives us a lot more data.
Yeah, I think the things that would be really interesting outside of the kind of the core ATS internals community would be tracking a histogram of requests against origins by origin. Like you can Because then you get, I mean, actually all of the outliers are no longer noise, right? It's that one user that calls and occupies your support staff because shit didn't load right. That noise is actually really noisy. So being able to verify that, like, oh, I do see you. You are in the long tail. Sucks to be you. As opposed to looking at it and saying, this is not our problem. There is no long tail for this service. There's no reason that you should have had that. That must be somewhere else other than ATS. So being able to disqualify issues is pretty valuable. Yeehaw.